Finite element analysis, or FEA, is a computational method used to predict how structures react to physical forces. It usually relies on standard Lagrange elements, but when we push these classical displacement-based models toward nearly incompressible limits, like simulating hyperelastic rubber, the math breaks. This failure is called volumetric locking. It occurs when a material's Poisson's ratio approaches 0.5. The Poisson's ratio is a measure of the expansion of a material in directions perpendicular to the direction of compression. At 0.5, a material is perfectly incompressible, meaning it cannot change volume. Standard elements respond to this by becoming mathematically rigid. This 2D Lagrange element shows why. Under bending loads, it produces parasitic shear, false internal strain vectors appearing at the integration points. The stiffness matrix can't resolve this. As values approach infinity, the solver triggers a matrix singularity error, hitting a zero-determinant state. These failures are incompatible with modern engineering requirements. We need simulations that handle multi-scale, multi-field problems, ranging from soft tissue biomechanics to complex structural instabilities during an earthquake. Classical displacement formulations are no longer sufficient for these complex boundary conditions. To maintain accuracy, we have to rebuild the solver architecture, starting at the element level. The first necessary upgrade is a shift away from displacement-only calculations. This diagram compares matrix structures. Left is the classical formula, relating stiffness and displacement to force. Right, the mixed method expands into a saddle point matrix, adding independent blocks for stress and strain. This parallel calculation decoupling prevents the artificial stiffness causing locking. Recent work on weakly symmetric mixed elements for elasticity has proven this approach remains valid, even at the incompressible limit. These formulations provide the reliability needed for high-precision structural simulations. However, locking isn't the only issue. We also have to address artificial hourglassing, a numerical instability where elements deform into zigzag patterns without absorbing any physical energy. To stabilize this, engineers modify the discrete green Lagrange strain operators. These operators are mathematical tools used to calculate strain in large deformation problems. By refining how these operate from displacement and using targeted strain operators, mixed formulations remove the artificial rigidity that causes numerical collapse. Even with stable elements, a fixed global mesh often fails when it encounters severe localized stress. This 2D gear shows localized stress. To solve this, HPQ adaptivity dynamically recalculates the mesh. H adaptivity shrinks physical elements specifically where errors are highest. P adaptivity elevates the mathematical polynomial order, moving from linear to quadratic curves, increasing accuracy without cluttering the entire model. Finally, Q adaptivity optimizes the numerical quadrature, the specific integration points within the elements, ensuring the math is as efficient as possible. Together, HPQ adaptivity allows the solver to focus its mathematical precision exactly where it is required, saving computational power in low-stress areas. Even adaptive meshing fails during phase changes. When solid soil becomes fluid, the physical connections in a standard grid snap and warp into chaos. To handle these scenarios, we move toward a different strategy: meshless methods. This approach removes the need for explicit connections between nodes. A prominent mesh-free technique is the Galerkin finite block method, or GFBM. This domain is defined not by a rigid triangle grid, but by overlapping continuous function zones. GFBM uses Chebyshev polynomials, mathematical waveforms that calculate the geometry without needing fixed edges or nodes. This flexibility allows the model to handle material discontinuities and changing boundaries without the heavy computational cost of constantly rebuilding a geometric mesh. By replacing rigid grids with continuous spectral polynomials, meshless methods protect the solver from catastrophic geometric distortion. This combined architecture, mixed elements, and adaptive meshing is what allows us to solve the three pillars of physical nonlinearity: geometry, material, and boundary conditions. For large geometric deformations, total Lagrangian and co-rotational formulations allow the local coordinate frame to rotate alongside the bending material. To solve these large-scale updates, the Newton-Raphson iterative scheme takes a stepped mathematical path, repeatedly refining until converging on the true nonlinear response. Material nonlinearities are handled by mapping complex constitutive models directly onto the adaptive elements. This includes the Mooney-Rivlin model, which provides the mathematical equations necessary to describe how hyperelastic materials react to high stress. We can even simulate fracture mechanics by coupling local finite elements with paradynamics. Paradynamics is a formulation that uses integration rather than derivatives, allowing the math to stay valid as microcracks propagate and branch through a material. This synthesis of mixed elements and dynamic discretization allows FEA to function as a framework capable of tracking total physical degradation. Resolving these numerical bottlenecks enables simulations that couple multiple physical fields simultaneously. A prime example is fluid structure interaction, or FSI. Here, a vibrating elastic plate is submerged in liquid. The fluid domain is modeled with boundary elements that interact directly with the finite elements of the structure. The solver simultaneously resolves the fluid pressure matrices and structural deformation matrices. The interface between them transfers pressure data into the structural matrix, which then sends displacement data back to the fluid. This coupled architecture is also used for biomedical implants. It simulates how electromagnetic fields from wireless chargers generate thermal loads in human tissue. It also applies to poroelastic materials, where we model how fluids move through and deform porous solid structures, like Arctic soils or biological membranes. By moving beyond the limitations of standard Lagrange elements into mixed, adaptive, and meshless regimes, finite element analysis provides a unified mathematical framework for simulating the coupled, nonlinear interactions seen in real-world engineering.